Math466, Advanced Applied Analysis, Lecture 30. Today we're going to finish up the joint density function for the 2x2 case and talk about how you generalize this to the n by n case. Up until recently, the only solution for the spacings between eigenvalues was when the eigenvalue densities were Gaussian. But there has been remarkable advances in the last decade. We can now prove this in almost full generality. We just need some weak assumptions about third or fourth moments. You will occasionally see me peering intently through the windows. It's because I'm seeing construction people walking by, and I just want to make sure that the demolition trucks go to the right building. There have been issues in the past. All right. So we had the following formula. We were looking at 2x2 matrices. And so we wrote A as Q transpose lambda Q. We assumed lambda 1 was greater than or equal to lambda 2. And at the end of the day, we got the joint density function for the eigenvalues. Probability of lambda 1, lambda 2 was some constant, lambda 1 minus lambda 2, e to the negative lambda 1 squared plus lambda 2 squared. Okay. And so the first thing we want to do is we want to figure out what is C prime. So we need to do the integration. So 1 should be the integral. Let's do lambda 2 goes from minus infinity to infinity. Then what's the range for lambda 1? Well, what am I assuming about the relationship between lambda 1 and lambda 2? So it would be lambda 2, and then it goes all the way up to infinity. So I would have lambda 1 minus lambda 2, e to the negative lambda 1 squared minus, plus I'll do lambda 2 squared in parentheses, d lambda 1, d lambda 2. So I could change variables. I could let lambda 1 equal lambda plus lambda 2, and now they would both go from 0 to infinity. So if I do this, I get 1 equals the integral lambda 2 goes from 0 to infinity, integral lambda 1 goes from 0 to infinity, and now I'll get C prime lambda e to the negative. Now lambda 1 squared is just going to be lambda plus lambda 2 squared. So I'll get minus 2 lambda 2 squared plus 2 lambda lambda 2 plus lambda squared d lambda 1, I'm sorry, d lambda 2. And this is just from replacing lambda 1 with lambda plus lambda 2. So if I look at this, this is beginning to look like a Gaussian up here in lambda 2. So I have a double integral. One of our best techniques for double integrals is to just switch the order. And so we'll do the integration over lambda 2 first. So we get C prime integral lambda equals 0 to infinity, integral lambda 2. Oh, sorry, lambda 2 is going from minus infinity to infinity. And lambda is going from 0 to infinity. So lambda 2 goes from minus infinity to infinity. We have a lambda over here, and then the lambda 2 integral is e to the minus 2 lambda 2 squared plus 2 lambda lambda 2. I'm sorry, plus lambda lambda 2 plus lambda squared d lambda 2. So this looks a lot like a Gaussian. I can put in the factors of 1 over square root of 2 pi. That's not so bad. Now, this is also looking almost like lambda 2 plus something squared. So if it's lambda 2 plus lambda over 2, because then when I square it, it'll come out right. So this is equal to just C prime. Did I make a mistake somewhere?
Well, do you have to multiply the...
Oh, sorry.
Yeah.
Thank you. And then this should be a minus like that. Right?
And then what if we do...
Yeah, I mean, I guess why do we want to leave the negative lambda squared outside? Are we going to use that complete square as well? Or?
Well,
So I guess now we're getting like a difference of squares.
we're gonna right, but we'll pull this outside to be the second integral. I can keep this in. Or what I could do over here is a better way of doing this to do it all in one step.
It's not dependent on the lambda 2, so we can.
Plus, I think lambda squared over 4. Or do I want over 4 or do I want over 2?
Negative 2. Negative 2? No.
Well, because don't I want lambda 2 plus lambda squared will be.
Well, yeah. No. Yeah,
Oh, okay.
It's over 2. Yeah. Well, because we're just factoring out the 2 right now. Well, now we've dropped the lambda squared.
No, yeah, but I'm saying, is this what I'm going to want for inside the square? Because I don't have it.
Oh, yeah, okay, I agree.
So then I
Now
want
you're gonna
this,
have another.
and then I'll have this one over here. Then it will be.
Lambda squared over 4 again. Right.
And then the 2 multiplies both of them, so this will be fine.
Yeah.
So I want to write lambda squared as twice lambda squared over 4 plus lambda squared over 4. This is just completing the square. And so now I'll get lambda e to the negative lambda squared over 2. And now I'll have the integral lambda 2 goes from minus infinity to infinity, e to the negative lambda 2 plus lambda halves squared divided by 2 times 1/4 d lambda 2 d lambda. And by writing it as 2 times 1/4, that's a half down there, and then it comes up. The reason I'm doing this is so that I can identify what the variance is of this Gaussian. So then I want to have a square root of 2 pi and then a 1/4, and then a square root of 2 pi 1/4.
Yep.
And so now this integral is just a Gaussian with mean lambda over 2 and variance 1/4. And that will now integrate to 1. So I will get c prime square root of pi halves, and then the integral lambda goes from 0 to infinity of lambda e to the negative lambda squared over 2 d lambda. This is a nice integral to do. What is this integral?
Sorry.
Yep.
Why are we dividing by 2 and multiplying by 1?
Over here?
Oh, that's the same as multiplying by 2.
This is the same as multiplying by 2.
And then the square root of 2 pi 1/4.
Right.
That's just 1, right?
This is just 1. And so the whole point is I want to write this as a Gaussian.
Okay.
And so I need the normalization constant of the Gaussian. And I need this to be of the form, e to the negative, lambda 2 minus its mean squared over 2 sigma squared. So sigma squared is going to be 1/4.
Okay.
Now when I do this integral, I can just do u substitution. This integral I think is just 1. What's nice is the 2 over here is exactly what I need to even cancel the exponent there. And so when I just integrate, I'll get e to the negative lambda squared over 2. And then because of the negative sign, I flip 0 and infinity. And so I just get 1. So this is just equal to c prime square root of pi over 2. Therefore, c prime should be the square root of 2 over pi. All right. We'll see in a little bit later another way to do this integral. But we now at least have the normalization constant. And the key thing to remember, because it's a while, this was I think the Monday before Thanksgiving, is that we didn't have to figure out what g of theta was. We didn't have to do the theta integration. Now that we have this, we can actually calculate what's the probability of a gap between the eigenvalues of equal to lambda. We now know the normalization constant. And so this leads to the following. So what is the probability that lambda 2 minus lambda 1 is in, say, lambda plus delta lambda? So if we can calculate this, we then just take the limit as delta lambda goes to 0, and that will give us the probability density for the spacings between eigenvalues. And that's what we really care about. How long do you have to wait for the next energy level? How long do you have to wait for the next hit? And so we would just want to integrate lambda 2 goes from minus infinity to infinity, lambda, and then integral lambda 1 goes from lambda 2 plus lambda to lambda 2 plus lambda plus delta lambda. We know what C prime is. It's just the square root of 2 over pi. We've got lambda 2, 1 minus lambda 2. So it'll just be lambda plus delta lambda, and then e to the negative lambda 1 squared. So lambda plus delta lambda. I'm sorry. Let me be a little bit careful. Let me just write it slowly. Lambda 1 minus lambda 2, e to the minus lambda 1 squared plus lambda 2 squared, d lambda 1, d lambda 2. So this would be calculating the probability that the difference is in lambda, lambda plus delta lambda. I then divide by delta lambda, take the limit as that goes to 0, and that will give me my probability density. If you want, you could also calculate the probability that's in the interval negative infinity to lambda plus delta lambda, subtract off the probability that's in negative infinity to lambda, divide by delta lambda. That's taking the derivative of the cumulative distribution function. Either way is fine. So this will give me the density of getting an eigenvalue of lambda, an eigenvalue difference of lambda. So let's look at what is going on. We are integrating here over a very small interval of size delta lambda. We're going to divide by delta lambda and send delta lambda to 0. So a term of size delta lambda will contribute in the limit because we divide by delta lambda. A term of size delta lambda squared will not contribute. The width of this interval is of size delta lambda. So we've already got something of size delta lambda just from the length of integration. All that really matters is the main term here. The delta lambda doesn't matter. It's going to be a lower order term. So the main term is just replace lambda 1 with lambda 2 plus lambda. The next term, you're putting in that next correction, well, that correction is going to be at most delta lambda. I then integrate that over something of size delta lambda. That'll be delta lambda squared. So similarly, up here, all that's really going to matter is the main term. And so what we get is that this is equal to the square root of 2 over pi lambda e to the negative, and now the main term is going to be lambda 2 plus lambda squared plus lambda 2 squared. I still have my lambda 2 integration. One plus something of size delta lambda, d lambda 1, d lambda 2, and lambda 1 is going to go from lambda 2 plus lambda to lambda 2 plus lambda plus delta lambda. So when I do the lambda 1 integration, all that really matters is the 1. The error of size delta lambda doesn't really matter. So I will get the integral lambda 2 goes from minus infinity to infinity, square root of 2 over pi, lambda e to the negative 2 lambda 2 squared plus 2 lambda 2 lambda plus lambda squared d lambda 2. This should look extremely similar to the calculation we just did. The calculation we did before was we integrated lambda 1 goes from lambda 2 all the way up to infinity. Now we're going from lambda 2 plus lambda up to infinity. I'm sorry, up to lambda 2 plus lambda plus delta lambda. We just want to know the probability in a small region. When the dust settles, it's going to be an extremely similar calculation. We complete the square exactly as before. We pull things out exactly as before. The only difference is now we don't have that lambda integration. the lambda 2 integration is going to be exactly the same. And so when the dust settles, this should just be the square root of 2 over pi, and it'll be lambda e to the negative lambda squared over 2. And we just complete the square exactly as before, see the lambda 2 integration as a Gaussian exactly as before, and that's our density. So if we have a 2 by 2 matrix, this is the probability of observing a gap of size lambda, the probability density function, assuming we choose our entries from a Gaussian. Compare this to the nightmare we had before when we used the quadratic formula. Right? Where we had square roots and we had sums and products and differences of random variables. And the difference was going to be square root of b squared minus 4ac all over a. So this is a much nicer approach. All right, now the question is, what happens if we go to an n by n case? Yes?
I guess I'm a little confused about how you got rid of that second integral and like why you added the
Which second integral? The lambda 1 integral?
yeah, the lambda.
Well, because
So it's going to be small.
I should probably put, and this is, up to errors of size delta lambda. So remember, we really want to look at not just the probability that we're in this interval, but the probability divided by delta lambda.
Oh.
And so this is what the calculation would be. I'm being a little cavalier. I really should then divide this by 1 over delta lambda and take the limit as delta lambda goes to 0. So if I then do 1 over delta lambda and take the limit as delta lambda goes to 0, these higher order terms won't matter. Because once you have a delta lambda squared, even when you divide by delta lambda, it's small. And so that's why this limit will actually be the same as what I get over here. So I'm being a little cavalier. The book, as you've read, goes through this in a little bit more detail and slowly shows what these probabilities are. This is the 2 by 2 case. The 2 by 2 case is a little bit misleading because we have 2 eigenvalues and only 1 angle. In the general case, it's very different. So let's look at a general n by n matrix. And we want to see how this changes. So now it's the n by n case. So A is still Q transpose lambda Q. This has n eigenvalues. Now, if A is a real symmetric matrix, this has n plus 1 over 2 free parameters. We have the diagonal, and then we have the upper triangular part, and then the lower triangular part is just filled in. So for an n by n matrix, there's on the order of n squared over 2 free parameters. Only n of the parameters are eigenvalues. So the angles, we have n minus 1 over 2 angles theta I. And when you take n equals 2, you get this just one angle and 2 eigenvalues. But in general, you will have more angles than eigenvalues. So the goal is we want to go from A11, A12, all the way to ANN, to lambda 1, lambda n, theta 1, theta n, and minus 1 over 2. So now we have to write down the Jacobian for this change of variables, integrate out the angles. Okay? I am assuming nobody wants to write down the Jacobian explicitly and determine even how Q depends on the angles. So This is very similar to the calculation we did before, and this is the main reason why I wanted to do this in the course. It's integrating without integrating. It's trying to just figure out what are the dependencies. So let's analyze what's going on. So A is Q transpose lambda Q. So we've got some theta dependence here. Then we have lambda 1 through lambda n. And then we have our thetas over here. And this is our A, ij. And now we need to calculate the Jacobian. We want the determinant of the Jacobian. Usually, if you're going to calculate the determinant of a matrix, it's important to know what the matrix is. Okay? We do not want to calculate what this matrix is. Let's think about how it will look when we multiply things out. So what I claim is this final quantity, each entry is linear in the eigenvalues. And the reason is when you do the multiplication out, I have a diagonal matrix with just lambdas down here. So when I do the first multiplication here, if I take the first column times this, I'll get a lambda 1 from that. Will I have anything else, any other lambdas coming into that first entry? To get the one over here, I'll have a lambda 2. To get the one over here, I'll get a lambda 3. So when I multiply these two matrices, I'm going to have something where each one of these is linear in the eigenvalues. The first entry here will only involve lambda 1. The first entry here will only involve lambda 2. The first entry here will only involve lambda n. Then over here, the first entry of this will only involve lambda 1. No, I'm sorry, will involve lambda 2. Because now I'm going to be taking the second column. So when I take the second column, sorry, it'll involve lambda 1. It'll involve lambda 1, lambda 1, lambda 1, lambda 1, lambda 2, lambda 2, lambda 2, lambda 2, lambda 3, lambda 3, lambda 3. So the first row here only involves lambda 1. The second row only involves lambda 2. The third row involves only lambda 3. So do we all agree that when I multiply these two matrices together,
Isn't it going to be the other way?
is it the other way? So if I take this column,
Maybe horizontally, like the first row will involve it.
well, the first row, first entry, is the first row here and the first column here, so I get just a lambda 1. Then the first row, second entry, is I take the second column, and when I take the dot product, I just get a lambda 1. So the first row of this matrix multiplication only involves lambda 1.
Yeah.
So this row only involves a lambda 1, and the last row only involves a lambda n.
Yeah.
Okay, and now when I multiply over here, I'm going to get something that's linear in the eigenvalues. Because this first row goes lambda 1 through lambda n. I've got something over here. I'm never going to get products of the eigenvalues. So at the end of the day, when I calculate this matrix, each entry is linear in the eigenvalues. So this is the key point. Do we all agree that each entry is linear in the eigenvalues? That when I just do this multiplication, the ith row only involves lambda I, and now when I take this, okay. So this whole thing, each entry is linear in the eigenvalues. So now let's look at the Jacobian. So here's the Jacobian. It's going to be a mess. So we have to take the derivative of all of our different transforms. So we have first dA11 d lambda 1 all the way down to dAnn d lambda 1. What can you tell me about the eigenvalue dependence in the first row of this matrix? Do any eigenvalues survive when I take the derivative with respect to lambda 1 in the first row? No, it's linear. Each matrix element is linear in the eigenvalues. So at worst, it has some constant times lambda 1. So when I differentiate, there's no longer a lambda 1, and if there was a lambda 2, that's sent to 0. So whatever these entries are, they are just massive, ugly functions of theta. We go all the way down to dA11 d lambda n, all the way down to dAn d lambda n. And all of these will also not involve any eigenvalues. So no lambda I. What about all the crap that comes below when we start differentiating with respect to the angles? So now we have dA11 d theta 1 all the way down to dAn d theta n. I'm sorry, d theta 1. And we keep going all the way down. What do we know, bless you, about all of these rows? Can they have eigenvalue dependence? Yes. But they have to be linear in the eigenvalues. So these are all linear in the lambda I. And that's because each entry is linear in the lambda i's. So when I differentiate with respect to an angle, if I had, 5 lambda 1 cosine whatever crap, when I take the derivative of the angle part, I'll still have that 5 lambda 1. So each entry here is still linear in the eigenvalues. Okay? So are we comfortable up to this point? The whole idea is to get enough sense of what the J looks like that we can calculate its determinant as some nasty function of all the angles times a really nice function of the eigenvalues. And then we just integrate out all the angles. Okay. Well, we know a little bit of something about this change of variables. So when you do a change of variables, when are you allowed to change variables from one to another? So if I have a relation between things, I can't always change variables. So for instance, if I have f of x equals x squared on the interval 0, 1, or negative 1, 1, I can't change variables. Why can't I change variables? So here, you give me an x, and I can clearly tell you what y is. If I give you a y, do you know what x is? It's not. The change of variables is not uniquely determined. We need to have our change of variables uniquely determined. We don't want a degeneracy. When is there a degeneracy? Well, if two of the eigenvalues are the same, things should break down. Let's look at the 2 by 2 case when two eigenvalues are the same. Say n equals 2, lambda 1 equals lambda 2 equals lambda. So we now get A equals Q transpose lambda lambda Q. Well, this is the same as lambda times Q transpose Q. But what's Q transpose Q? It's the identity. So we just get so no matter what Q I put in, if the eigenvalues are the same, I get back the same matrix. What this means is I can't pass uniquely from the elements of A to my theta lambda 1 lambda 2 in this case. The transformation breaks down. Right?
Yeah.
you give me a matrix A and ask, well, what does it look like in theta lambda space? Well, if the two eigenvalues are the same, you actually have infinitely many choices. In fact, any angle works. Crap. Well, this is actually good for us. Things should break down when two of the eigenvalues are the same. How do things break down? What's going on? It means the determinant is 0. The derivative is 0, essentially. Now, the Jacobian is the matrix of derivatives. If you think back to the x squared, its things are breaking down at x equals 0. So when we look at our transformation, things should break down whenever eigenvalues are the same. So if the eigenvalues are the same, and we want things to break down, the determinant should be 0. So the determinant of this matrix should be 0 whenever two eigenvalues are the same. Otherwise, we would be able to invert, and we should not be able to invert. If two eigenvalues are the same, we shouldn't be able to go back and forth. So does everyone agree that the determinant of J must be 0 if two eigenvalues are the same? Okay. So we're now making a lot of progress. So we have the determinant of J is 0 if two eigenvalues equal. So that means I should be able to write the determinant of J as some function of theta and lambda times a product 1 less than equal to I less than j less than equal to n of lambda j minus lambda I. And the reason is whenever two eigenvalues are the same, it has to be 0. It's got to have a factor like this. And then whatever's left over, it could unfortunately still involve the lambdas. And it has to involve the thetas. What do we hope is true about this function g of theta lambda? What would we love to be true about this function? So we would definitely love it to be constant, but I think that's asking too much. Also, I think asking too much. How would you like it to depend on lambda? So it's too much to ask it to be constant. Linear would still be painful. How would you like it to depend on lambda? We succeeded in the 2x2 case because we were able to write the Jacobian as some function of theta times lambda 2 minus lambda times lambda 1 minus lambda 2. So over here, how would we want this to depend? And actually, I guess I was doing the lower minus the higher, so I guess I should do, doesn't really matter, lambda I minus lambda j. And just to be the same notation as what we did before. We would like this to be independent of lambda. If this is independent of lambda, then we can just integrate out the thetas. And here's the lambda dependence. So the hope is that this doesn't depend on lambda. And if that's the case, then we have a really nice expression for our Jacobian, because we don't care about the theta dependence. And the reason is we showed that the probability of a matrix in the 2x2 case was constant e to the minus trace of a squared. That's still the case in n dimensions. The probability of our matrix A is some constant e to the minus trace of a squared, which is just a constant e to the minus lambda 1 squared plus lambda n squared. So this is in the stuff you should have read for today. Notice that the probability of the matrix doesn't depend on the thetas. It only depends on the trace of a squared. It only depends on the sum of the squares of the eigenvalues. If we can somehow split the Jacobian into an angular part and an eigenvalue part, then we can just integrate out all the angles, and that'll just be some normalization constant. So it all comes down to, can we show that this doesn't depend on lambda? All right, well, this is going to be a polynomial in the lambdas. What is the degree of this piece? Yn. So when I multiply this out, it's going to be a massively messy expression involving the lambdas. And I have a product 1 less than equal to I less than j less than equal to n. So I'm essentially asking how many terms are there in the product. Each term increases the degree of this polynomial by 1.
Well, or n minus 1. Because, like, I can only go from 1 to n minus 1.
Right? But then for each choice of I, you can take any j. It's n choose 2. I choose 2 numbers from 1 to n that are distinct. So the degree is n choose 2, which is n minus 1 over 2. So this is a polynomial of degree n minus 1 over 2. Let's go back and let's look at the Jacobian. Let's go back over here and try to get the camera to follow. And look at the Jacobian. There we go. All right, excellent. So when we come back over here, this is how I get my steps in for the day. We looked at this matrix. The first n rows do not involve lambdas. The last rows do. Okay? Each of these rows is linear. When we calculate the determinant, we choose one element from each row and each column, and we look at all the different possibilities. So you remember your formulas for determinants? Right? Yes? Looking at the permutations and figuring out what the sign of the permutation is. Right? Well, how many rows do we have where there's a possibility of having a lambda? It's the angles, right? The theta 1 through dA11 d theta n minus 1 over 2. So the number of rows we have where we can have an eigenvalue is n minus 1 over 2. So when you look at this, the maximum polynomial this could be in the lambdas is of degree n minus 1 over 2. So we know maximum degree in the lambda I is n minus 1 over 2. So we know it can't be more than that. But looking over here, all right, so we know that's maximum n minus 1 over 2. Let's see if we can get the camera to follow. Nope, that's all right. I need the steps. All right, and so the maximum is n minus 1 over 2. But over here, we show that this is already n minus 1 over 2. There can't be any more lambda dependence. So we know that this actually is independent of lambda. And then the rest of the argument is the same as before. We can now integrate out all the angles, and now we have a joint density function that's very nice. And you can calculate normalization constants as before. It's a little bit more involved now that it's n by n. You have to do a little bit of work to show that the probability of the matrix is what is claimed over here. We did the 2 by 2 case. If you have a general n by n case, what you want to do is say, all right, well, let me do an infinitesimal rotation with maybe aii, ij, ji, and jj. Or if you want, you can say, well, you know what, without loss of generality, I can assume I is 1, j is 2, and then just use the results from the 2 by 2 case. You know, I talk about this in the book, so I will let you reread that again. You get the same density as before. We now have the Jacobian exactly as before. We can integrate out the theta exactly as before. It's worth thinking about, you know, what we accomplished here. This is truly remarkable. How many of you remember your polar coordinates? All hands should be up now. All right, you can't not remember polar coordinates. Spherical coordinates. How many of you remember spherical coordinates? Or could get spherical coordinates without too much trouble? How many of you know the coordinates for the hypersphere, you know, or the n-dimensional sphere? in the n dimensions. So there are formulas for what happens if you're in a four-dimensional space and you have a sphere. They get a little bit worse, but they're not too bad. We are not writing down explicitly what these theta matrices are. It's this sum orthogonal transformation with n minus 1 over 2 free parameters. It's becoming a nightmare. But what's great is we do not need to know the details. We just needed to figure out what is the dependence. And this is a great thing to sniff out in mathematics. This is end of the semester, last chance to really tie things together. This goes back to linear algebra. And we don't need to know things perfectly. We just need to know things well enough to then say integrate out the rest of the crap. All right, so we've got about 5 minutes left. I want to end the day with something similar to what we're doing here. So here's a challenge. It's a linear algebra challenge. I want to construct a matrix that has n rows and infinitely many columns so that any n columns are linearly independent.
Wasn't this like a homework problem in operations?
I think this was a homework problem in operations research. I think we've done this before. But it's fitting to put it in here right now.
Yeah.
So one thing you can do is you can say, well, let me choose my first column.
Yep.
And now I choose something that's not along that line. The probability that I choose something that's not along that line is essentially 100%.
Yep.
These two objects now span a plane. I now choose something that's not in that plane. Again, probability is 100%. And now I keep going like this. So let's say n equals 3. Now I want to choose a fourth direction. Well, I look at the plane spanned by these two and I make sure it's not in that plane. I look at the plane spanned by these two and I make sure it's not in that plane. And I look at the plane spanned by these two and I make sure it's not in that plane. And I put something in. And so what I keep doing is I keep looking at all pairs. That gives me a finite number of planes at each stage, and almost all vectors will work. So what's nice is if you choose a matrix at random, with 100% probability it works. The nice, fast, explicit construction is the following. Choose 1, x1, x1 squared, all the way up to x1 to the n minus 1. 1, x2, x2 squared, all the way up to x2 to the n minus 1. 1, x3, x3 squared, all the way up to x3 to the n minus 1, and so on and so on and so on. When you look at any n columns, you'll have just n things like this. And this is called a Vandermonde matrix. And so when I look at this, let's say I'm just looking at a 3 by 3 case. If any xi equals another one, so if x1 equals x3, the columns are linearly dependent. You can then show that that's the only way that you will have the determinant be 0. And as long as the determinant is not 0, you win. So explicitly, if we choose n columns, without loss of generality, I'll label them x1 through xn. 1, x1, x1 to the n minus 1, dot, 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 1, xn, xn to the n minus 1. And I want to take the determinant of this. This is clearly going to be a polynomial in x1 through xn. If any x equals another x, it's 0. So this has to be a multiple of the product 1 less than or equal to I less than j less than or equal to n of xi minus xj. This is exactly the quantity we were looking at a moment ago. The degree here, as before, is n minus 1 over 2. What's the degree of this polynomial going to be? I choose something from the first row, something from the second, something from the third, all the way up to something from the nth. So the degree is going to be 0 plus 1 plus n minus 1, and that's equal to n minus 1 times n over 2, which is the same thing as this if you just flip the order of multiplication. So they have the same degree. So the only thing that the multiple can be is some constant. So this has to equal a constant times this. All you need to do now is show that the constant is non-zero. Well, what you can do is you can just choose the x's so that they're growing so rapidly that the main term is the main diagonal. So choose, x1 much, much less than x2, much, much less than x3, much, much less than xn. And then the diagonal term will be the largest because it has the highest power of x to the n, of xn. So as an exercise, make this explicit. I think if you do something like, xj plus 1 is 100 factorial to the j plus 1 factorial, do some absurd things like this. It's going to be growing so rapidly. Or do things as a tower. xj plus 1 is 100 factorial to the xj. And start off with, x1 is 100 factorial. Do something like this, and it's going to grow so rapidly that the main term can't be killed by everything else. And you'll even get that this constant has to be 1. So the idea we used here about looking at getting this matrix as a product of differences is something that occurs in a lot of different things. All right, this is a good place to stop. Wednesday's class is going to be a little bit shorter so that there's time to do SES forms. And then Friday is, I'm sorry?
That's already happening.
That's already happening. And then Friday will probably be the uncertainty principle, but I can't be sure.